In this video, we're going to look at the gas laws and some simple ways to make an estimation of what will happen when we do this. We won't be doing full calculations like we do in other classes, but in this class we're going to estimate whether something increases or decreases. In order to understand the gas laws, we need to know that there are 4 variables that are used to describe a gas, and then we're going to look at how they interact with each other. The first variable we have is pressure. Pressure is measured in atmospheres or torr, and it is how much some gas is pushing out or pushing on other things. So when we look at our tire, we see the pressure of the tire, and the gas particles are pushing up, down, left, and right. They're pushing in all directions. And so we know that the pressure is something we can measure. Next, we have the volume. So we're going to use the letter V for volume. This is going to be measured in either liters or milliliters. I commonly use liters, but it can also be done in milliliters quite often. So this is going to be how much gas we have. It's a big container or a small container. For our work with gases, because gases completely fill the container, we can understand that the volume of the container will be equal to the volume of the gas. Next we have N, and N is kind of a weird one. N is the number of particles. That means how many there are. So it's just a number, and that means that we're going to be using the word mole. So mole is a number. Again, it just tells you there's 6.02 times 10 to the 23rd of whatever it happens to be. So we're going to be using that number in moles, and it will be more like 1 mole, 3 moles, something like that, rather than number of particles. And the last one is T for temperature, and that is going to be always measured in the Kelvin scale for all of these gas laws. There might be a time that we're given a number in Celsius, so we need to convert it to Kelvin, or we might go from Kelvin to Celsius. In this class, we will not be doing anything in Fahrenheit, though you could possibly be asked a question in Fahrenheit. The way that we use this is just to say, is it going to increase or decrease, so the actual numbers won't make a difference whether you use Fahrenheit, Celsius, or Kelvin. They will all go the same direction. So those are the 4 things that describe a gas, how we can decide how big it is, what the pressure is, how many particles, and the temperature will completely describe all the characteristics of that gas, other than color, smell, toxicity, those types of things. But all the things that we need for all the calculations will be described by these 4 factors. Most of the gas laws will be looking at these 4 factors and seeing how they relate to each other. So we might look at pressure and volume, pressure and number, pressure and temperature, volume and number, volume and temperature. We could look at any of those 4 and make a comparison. We're going to talk about 6 different gas laws that we study in this course. The first 4 are very separate from each other. The 5th one takes all of those and combines them, and then the 6th one is completely separate again. I will not be asking you the names of the gas laws, so I won't say what is Boyles Law, but I will be asking you to know how they relate to each other. So we're going to look at Boyles Law, it's the first one, and that one says that the pressure is related to the volume. In Charles' Law, the volume and the temperature are related. In Gay-Lussac's law, the pressure and the temperature are related. Avogadro's law, the number of particles and the volume are related. The ideal gas law puts all of those together, and it relates the pressure, the volume, the number of particles, and the temperature all together. And then finally we look at Dalton's law of partial pressures, which is completely separate from the others. One thing to note on each of these relationships is that there's this little alpha sign. Now the alpha means proportional to. Things can be either directly proportional or inversely proportional. And we're going to look into that a little bit more. So what are directly and inversely proportional? First we need to know, what does proportional mean? What we mean by proportional is that they go in equivalent amounts. So if it increases by 1, they may both increase by 1, or I might increase one by 1 and the other one by 2, and then every time I do it, it always is double or triple or quadruple, whatever the number is. So we can see these types of graphs, one goes up, the other one goes up. And that's what we call directly proportional. They're going the same direction. So as one goes up, the other part of the graph is also going up. Inversely proportional says as I increase one, the other one decreases. One example of something that might be directly proportional is that every year I get 1 year older. So those are both going the same direction. Now in that case, as I increase 1 year, my age goes up by 1 year. So those are directly proportional and also equivalent. So let's try something a little bit different. What if I were to buy a melon for $2? If I bought 2 of those melons, that would now be $4. If I bought 3, it would be $6. So you can see that they're both increasing. They're both going in the same direction, so we call them directly proportional. But notice that the price is going up by 2 every time I buy an additional melon. So I buy 1, it's 2. If I buy 2, it goes up to 4. If I buy 3, it goes up to $6. So we're increasing it by 2. That means that they're related to each other, but they're not equivalent. And that's what we call directly proportional. And now let's look at something for inversely proportional. Again, inversely proportional says that as I increase one thing, the other one is going to go down. So for example, the farther I drive, the less gas I have in my car. If I drive 100 miles, I might use 5 gallons. If I drive 200 miles, I might lose 10 gallons. So as I increase the distance, I'm going to decrease the amount of fuel in my car. Notice in this case that the numbers are not equivalent to each other, so it's not going 1 for 1, but they are related to each other. So while I increased the mileage by 100, I only decreased the fuel by 5. So again, they're related to each other, but they don't have to be equivalent to each other. And that's what we call inversely proportional. One goes up, the other one goes down. So let's start with each of the laws now. We'll start with Boyles Law. In Boyles Law, it is stated that the pressure of a fixed quantity of a gas is inversely proportional to its volume at a fixed or constant temperature. So when we say constant, that means it's staying the same, and when we say fixed, it's staying the same. As we're reading this, we can see that there's a relationship between the pressure and the volume. So those two are related to each other. And the relationship says they're inversely proportional. Inversely means they go the opposite direction. We do have to do this when we have a fixed quantity of gas. That means we can't change the amount of gas. Quantity is a way of saying number. And same temperature, so we're not changing the temperature. In reality, we could change any of those at the same time, but we're keeping it simple, so for now we're just saying 2 of them are constant, 2 are changing. So here we're saying the pressure and the volume are inversely related, and you can think about this in this simple way. When you push on something, you'll notice that it squeezes and it goes down. So that's telling us that the pressure is increasing, that's your pushing, and that the volume is decreasing. So we know that they're going in opposite directions. They are inversely proportional. Now let's read through the sentence and see what we can get from this. It says that the pressure, so we're going to be looking at pressure, at a fixed quantity. So that fixed quantity is the letter N. It is the number of particles. We're going to put this letter C there just to say that it's constant. So N equals C is inversely proportional to the volume. That's the other one we're going to look at a fixed or constant temperature. So we're going to put a little C for the temperature, and so we can look at just the pressure and volume. And because it says it's inversely proportional, that means as I increase the pressure, I'm squeezing on something, what's going to happen to the volume is it's going to decrease. Now what happens if I release that pressure, so the pressure is less, then that means that the volume will increase. So we see both the directions. Increase the pressure, decrease the volume. Decrease the pressure, increase the volume. And of course we could go the other way. We could say, well, what happens if I pull on it and I make the volume larger? That's going to decrease the pressure. So you can look at it in both directions. Now let's look at Charles' Law. Again, you do not need to know the names of the laws, just the relationships that they have. In Charles' Law, the volume of a fixed quantity of gas is directly proportional to its absolute temperature at a fixed or constant pressure. So this is telling us that we're looking at the relationship between volume and temperature. It also says that it's directly proportional, which means they go the same direction. But what do we have to make that true? We always have to have, in this case, the fixed quantity. That means the number of particles is the same, and in this case, a fixed or constant pressure. So the pressure will stay the same. To help you visualize this law, we're going to look at a hot air balloon. So when a hot air balloon is cold, it lays on the floor and it's all kind of flattened out. Then they blow some air in it. That's not yet Charles' Law. But then they add some heat to it. So once they add the heat, you can see with that burner turns on, then the balloon gets larger and larger and larger. So the volume is increasing as they add heat to the balloon. When they cool the balloon, the volume decreases again. It increases and decreasing depending upon the temperature. Now let's read through the statement and see what we can find. So it says the volume, this is the thing we're going to be looking at, of a fixed quantity. Fixed means constant. Quantity is the letter N. Of a gas is directly proportional. That means they go the same direction to the absolute temperature. Absolute temperature is the temperature in Kelvin, because we're going to be using Kelvin. It won't make much of a difference as long as we know if it increases or decreases for us. But still, we want to always just remember, oh, we're going to do this in Kelvin. And so is proportional to its absolute temperature. That's the other part of what we're figuring out. And it says at a fixed or constant pressure. And so that means pressure, of course, is constant. So we're only looking at how volume and temperature are related to each other. As the volume increases, what's going to happen to the temperature? The temperature should increase. So we could take that balloon and just stretch it somehow. We would find that we would get an increase in temperature to go with that. And again, if the volume decreases, so we squish on there, then the temperature will go down because they go the same direction. You can change either the volume or the temperature. The balloon example, we increased the temperature, and that increased the volume, or decreased the temperature and decreased the volume. Now let's look a little bit at terminology. So if I say the volume, one of the terms that we might use is it expanded. And so if I say expanded, of course that means it is an increase. When we look at temperature, the terms that we might use are heated and cooled. Heated is an increase in temperature. Cooling is a decrease in temperature. So you want to keep that in mind when you're going through the questions. And finally, we'll talk about the last of the 4 individual gas laws, and this one's called Avogadro's Law, and it states that the number of moles of a gas is directly proportional to its volume at a fixed or constant temperature and fixed or constant pressure. So we're keeping the temperature and the pressure both constant, and we're only looking at how the number of particles and the volume of those particles will affect each other. The most common application of this every day is blowing up a balloon. So if you take a balloon and it's uninflated, it's flat, and you blow into it, you're adding gas to it. That's your number of particles. And as you do that, the size of the container will get larger. So the balloon will get larger as you blow air into it. I'm sure you're all completely shocked by that fact. And what happens when you release the air from a balloon? You let the air out, and the balloon shrinks back to its original size. So now let's read through this statement to see what we can get from it. It says, the number of moles, that's our letter N, of a gas is directly proportional. That means they go the same way to its volume. So we're looking at the volume, and we're going to see that those two are related, the number and volume, at fixed. So that means it's constant, it's not changing. Temperature, so put a little C with temperature, and pressure, we'll put a C for pressure. That means we're looking at the volume and the number. And again, you can go in either direction. The example of balloon says we're adding particles, we're blowing it up, so that's N is increasing, and V will of course go up in the same direction. And if we release that air, the number of particles will go down, and that means that the volume will also go down. What if we change the volume? Basically, if I increase the size of a balloon by pulling on it, somehow it will suck air into it so that the number of particles will increase inside. And again, if we squeeze that balloon and let out the particles, if they're available to be released, if you squeeze them out, the number of particles will get smaller. When we put all 4 of those gas laws together, we come up with something called the ideal gas law. The ideal gas law says that the pressure times the volume will give us the number of particles times the temperature times some kind of constant. It usually has an R here, but we're just going to say that they're related to each other. In this class, we are not going to give the actual numbers. All you need to know is how it increases or decreases, so which direction it goes. To do all of these, what we're going to do is we're going to take 2 of them as constants, and 2 of them will be changing. One will tell you the change. We're going to see what the relationship is to the other one. Because all 4 of the other laws are combined here, it's easiest to use just this equation and not go back and do the math for the other ones. So I'm going to show you everything I do on this chart. Now let's look at how we can use this chart to solve some problems. So this chart is basically allowing us to have two sections. On the left side we have the pressure and the volume, and they're going to be multiplied. So I'm going to put a little X here between them, and then we're going to see that that is related to, so that's proportional to, the number times the temperature. Instead of having a proportional to, I'm going to go ahead and put in an equal sign. They are actually not equal, but because most people in this class are much more comfortable with equals, I'm going to go ahead and put an equal sign so you can see how they're related. The reality is that there is a multiplier there. In most classes we would have the letter R, but we're just going to see, is it increasing or decreasing, so we don't need to know what that multiplier is. Is it being multiplied by 2 or by 0.2? That makes a huge difference in the answer, but we're not going to be looking at that specifically. But for me, I like to put in some numbers because it's easier for me to see these numbers. But because I like to keep my math simple, I'm going to use very simple numbers. So I'm going to put in 10 for the pressure, and 10 for the volume, and 10 for the number, and 10 for the temperature. So we know that 10 times 10 is equal to 10 times 10. Let's just kind of keep things started, and we're going to look at how we can compare it to those numbers. So if I say that the pressure is constant, that means that we're going to say it's constant. We're going to put a letter C there, but what that means is if I started with 10, I'm going to go ahead and put 10. Then I'm going to say that the volume is increasing. I'm just going to put an arrow up, and I'm going to pick a number larger than 10 because I've increased the volume. So in this case, I'm going to go ahead and jump it up to 20. That's a definite increase. We can see how easily it goes. And the reason I use 20 is just because the math is simple. Then we're going to look at the number of particles. Let's say the number of particles is constant. If it's constant, that means it'll continue to be 10. And then we look at the temperature. We're going to decide, does that go up or down? So we saw that the volume went up. We see that 10 times 20 is equal to 10 times what number? And we should see that that should be 20, and that's higher, so that means that the temperature has increased. All right, let's try another one. So in this one, I'm going to change the pressure. The pressure I'm going to say is decreasing. The volume is going to be constant. The number of particles is going to be what we're looking for, and the temperature is going to be constant. So we're going to put an arrow down for pressure. We're going to put volume. We're going to put constant. We're going to put number of particles is the thing we're looking for. We're going to find out what happens there. And the temperature is going to be constant. So for pressure, we're going to put in a number that's lower than the original 10. I like to pick 5 because 5, 10, 20, those are easy numbers to work with. So I know 5 I'm going to put there. All I have to do is pick something less than the original 10 because it has decreased from the original, which we picked as 10. And then the volume we're going to put constant, so that's going to be 10. And then the number is what we're looking for. And the temperature is going to be constant, so it's going to be a 10. And looking at the math, then we see that 5 times 10 is equal to something times 10. And hopefully you can see in the math this is going to be the number 5. So n is now 5. It originally was 10. That means it is less, so it has decreased. N is decreasing. All right, so what happens if I know that I'm going to increase the temperature, and I know that the number of particles is constant, but I want to find out what happens to the pressure, and the volume is constant, okay? So we're kind of reading it a little bit different. Of course, it can be in any order. We just need to know what we put where. So we just now said that where temperature is increasing, we'll put an up arrow, and we're going to go ahead and pick a larger number than 10. We're going to put a 20. We said the number of particles was constant, so we'll put a C there, and that means it's going to be 10 because we're looking at the 10 comparison. We're saying that the volume is constant. That's a letter C, or the number 10. And we're looking to find out what happens to the pressure. So we're looking to find out what happens on the left side. What we're going to see then is that N and T, that is going to be 10 times 20 is equal to 10 times what number? Hopefully you get 20, which indicates that the pressure has increased. It used to be 10, now it's 20, so that's an increase in pressure. Now I'm going to have you try one. We're going to have the number of particles decreased. We want to find out what happens to the volume if the pressure and the temperature are constant. Go ahead and try it, assuming that all of the original numbers were 10, what we put in each of those places, and then try to discover what the answer is. So hopefully you're ready to go. You should have had n goes down, so it becomes something like 5. The temperature and the pressure are both constant, so they'll both be 10. And the volume is what we're looking for. So we have 5 times 10 is equal to 10 times what? And that should be 5, so that means that the volume has decreased. So far, everything we've tried has had the things that are changing on opposite sides of the equal sign and the things that are constant on opposite sides of the equal sign. Now let's try one where they're both on the same side. I'm going to skip a line in the chart just to kind of keep these two groupings separate. I want to see what happens. So on this one, I want you to say that the pressure is increasing. We want to find out what happens to the volume, and this is going to be at constant number and temperature. So we're going to put constants. We're going to put in tens, 10 here, 10 here, and then for pressure, we're going to say it increased. I'm going to go ahead and put a 20 there. And so we're going to have 20 times what is equal to 10 times 10. 10 times 10 is 100. 20 times what is 100. We're going to have to pick the number 5. So 20 times 5 is 100, and that is equal to 10 times 10. So these are a little bit harder because you have to think about the math a little. But again, I'm using simple numbers to make sure that I'm going the right direction. So we saw the pressure increased. The volume has gone down because it was 10 and now it's 5. So we know that the volume is decreasing. Let's try another one. Let's say in this case, I know that the pressure and the volume are both constant. I'm going to go ahead and put 10s for pressure and 10 for volume. And then I'm going to say that the number of particles decreases. So for that, if I'm picking a decreased number, again, I like to keep it simple. I'm going to go ahead and use the number 5. What happens to the temperature? So we see 10 times 10 is equal to 5 times what? 5 times 20 is 100, so we know that the temperature will be 20 for this fake math problem, and that means that the temperature has increased. Let's try another one. What happens if we know that the volume decreases? We want to find out what happens to the pressure when the temperature and the number of particles are both constant. So we're going to put 10 for number of particles, 10 for temperature, and we're going to put for volume, I just said it decreased, so I'm going to pick the number 5. That means that the pressure must be what? So we have 10 times 10 is equal to 5 times what? And that would be 20. And I'm going to have you guys try the last one. In this case, I'm going to tell you that the temperature increases. We want to find out what happens to the number of particles. We know that the volume and the pressure are constant. I'm going to pause the video while you try this. So here's what we know. We know that the pressure is constant. We're going to go ahead and put a C there, and then number 10. The volume is constant, and again a C with a 10. We said that the temperature increased, so put an up arrow there, and we're going to put that as 20, and we're going to try to find N, which is what we're looking for. And so 10 times 10 is equal to something times 20. It looks like N is 5, so that means it has decreased. So for these 4 examples, what we found is that we were looking at two things on the same side of the equation. So we looked at the pressure and the volume, or we looked at how the number and the temperature were related to each other. Those are on the same side of this proportional sign or equal sign. So what happens when we do that? Well, what we see is that if they're on the same side, those two things go in opposite directions. So if you absolutely hate using numbers and you don't want to see the 10 times 10 and the 5 times 20 type of problems, then you can just memorize the patterns. So what the pattern is, if you look at the first 4, we see that if the two things are on opposite sides of the equal sign, or opposite sides of this little proportional or equal sign, we will see that they go in the same direction. So if one goes up, the other one goes up. If one goes down, the other one also goes down. And if they are on the same side, they go in opposite directions, where one goes up, the other one goes down. Or if the one that you're given goes down, then the other one must go up. I'll have another video where we'll get to practice more of these problems. But for now, we're going to go to the last of the gas laws, and that is Dalton's law of partial pressure. Dalton's law of partial pressure states that the total pressure exerted by a mixture of gases is equal to the sum of the pressures of the gases present. Basically, they're saying if I squeeze with one hand and then another person squeezes with another hand, then that means that the total will be equal to both of those hands pushing on something. So whatever it is, we're going to look at the total pressure. All you have to do is add them up. For these questions, there are essentially two types of problems you'll see. The first type is finding the total pressure, and for that we have to give you each of the individual pressures. So let's say I told you that the pressure due to oxygen was 10 atmospheres and the pressure due to the nitrogen was 20 atmospheres. What is the total pressure? Because we just add them together, we would see that the total pressure is 30 atmospheres. That's our pressure in this container. The second type is to say, well, what is the pressure of an individual particle if I know the total and I know the other particles? For example, if I said that the total pressure was 5 atmospheres and I knew that the oxygen had 2 atmospheres and the water was 1 atmosphere, how much is the pressure of the nitrogen if there's only oxygen, nitrogen, and water present? All you would do is take your total atmospheres, which we said was 5 atmospheres, and subtract out all the things that we know. So we know that the oxygen is 2 atmospheres, and we know that the water was 1 atmosphere. So 5 minus 2 minus 1 leaves us with 2 atmospheres for the nitrogen. Those are the two types of problems you'll see for Dalton's law of partial pressures in this class. And what we might see is that the number of gases can change. So notice that in the first one I only had 2 gases, in the second one I had 3. There can be many, many gases. In reality, there often are. But what we're looking at is the total will be equal to the sum of all the parts. That's it for the gas laws. I'm going to make another video that gives you some practice or shows you how to practice through these so you can see how to do the math and what the questions will look like.